Today we are going to discuss some important aspects related to coordination compounds. But before proceeding, let us discuss what we have learnt in last lecture. In last lecture, we learnt about interpretation of experimental data by Werner, effective atomic number, charge on a complex, coordination entity, central atom or ion, ligands and classification of ligands on the basis of charge. In continuation, today we are going to discuss classification of ligands on the basis of number of donor sites, chelate complexes, the chelate effect and thermodynamic stability of chelate complexes. Now, ligands can also be classified on the basis of the number of donor sites. When a ligand is bound to a metal ion through a single donor atom as in Cl-, H2O or NH3, the ligand is said to be unidentate or monodentate. Dent is a Latin word which means tooth, and when a ligand can bind through two donor atoms, as you can see in ethylene diamine or ethane 1,2-diamine or oxalate, these are known as didentate or bidentate ligands, that is two-toothed ligands. In ethylene diamine, you can see there are two nitrogen atoms which act as donor atoms, and nitrogen atoms at the end of the molecule have lone pair of electrons that can form coordinate covalent bonds. In forming a complex, ethylene diamine molecule bends around so that both nitrogen atoms coordinate to the metal atom M. As ethylene diamine is a common bidentate ligand, it is frequently abbreviated as EN. Here you can see another bidentate ligand, oxalate C2O4 2-. When several donor atoms are present in a single ligand, the ligand is said to be polydentate ligand. Polydentate ligands that bond through three donor atoms are called tridentate. Those that bond through four donor atoms are called quadridentate or tetradentate ligands. The ligands binding through 5 donor atoms are named as quincdentate or pentadentate, and hexadentate ligands are those which bond through 6 donor atoms. Here you can see the examples of polydentate ligands. These two are bidentate ligands. Here it is ethylene diamine with 2 donor sites, oxalato with 2 donor sites, dimethyl glyoxime, again a bidentate ligand, glycinato, 1 donor site at oxygen and 1 donor site at nitrogen. Here is a tridentate ligand, diethylene triamine, abbreviated as DIEN. Here are 3 lone pairs at 3 nitrogens. An example of tetradentate ligand is triethylene tetraamine, abbreviated as TRIEN. EDTA, that is ethylene diamine tetraacetate, is a very important hexadentate ligand. EDTA has 6 donor sites, 4 at oxygens and 2 at nitrogens. Now, you are able to classify ligands on the basis of the number of donor sites. There is another very important class of ligands known as ambidentate ligands. A ligand which possesses 2 donor atoms, but in forming complex it utilizes only 1 atom depending upon the condition and type of the complex is called ambidentate ligand. For example, NO2 known as nitro and ONO known as nitrito are ambidentate ligands. When nitrogen form a coordinate bond to metal, it is known as nitro, and when oxygen form coordinate bond, it is known as nitrito. Similarly, in SCN, when sulfur form bond to metal, it is known as thiocyanate, and when nitrogen form bond to metal atom, it is known as isothiocyanate. As you know that we have defined polydentate ligands earlier, there are some interesting facts related to polydentate ligands. When polydentate ligands bind to the central metal ion, they form a ring called chelate, and the ligand is referred to chelating ligand. EDTA, that is ethylene diamine tetraacetate, is an important chelating ligand. It has 6 donor sites, 4 at oxygen atoms and 2 at nitrogen atoms. Chelating ligand give rise to some special type of complexes known as chelate complexes. Now, complexes that consist of a metal atom or ion and polydentate ligand are called chelate complexes. Chelate complexes tend to be more stable than similar complexes containing monodentate ligands. The hemoglobin molecule in red blood cells is an example of a complex with a quadridentate ligand, or we can say tetradentate ligand, the one that bonds to the metal atom through 4 ligand atoms. Hemoglobin consists of a protein, globin, chemically bonded to heme group. You can have a look in this figure. Heme is a planar molecule consisting of iron 2 plus bonded to 4 nitrogens. In this figure, individual atoms are not shown. The 4 heme groups, here you can see the 4 heme groups in a hemoglobin molecule are represented by discs. Each heme group contains 1 Fe2 plus ion and porphyrin rings. A single red blood cell contains more than 265 million hemoglobin molecules and more than 1 billion Fe2 plus ions. Here is the structure of tris ethylene diamine cobalt 3 ion. This is ball and stick model. You can see 3 ethylene diamine ligands are bonded to cobalt and there are 3 rings. This is another form of the same complex. In this type of notation, nitrogen stands for ethylene diamine. Metal EDTA complex is a very important example of chelating complexes. Here you can see metal is bonded to EDTA ligand through its 6 donor sites forming rings. Now, as you have understood chelating ligands, so you can very well easily understand chelate effect. Now, the chelate effect describes the enhanced affinity of chelating ligands for a metal ion compared to the affinity of a collection of similar non-chelating or monodentate ligands for the same metal. For example, if we take 2 complexes, one with chelating ligand and one with monodentate ligands, you can see copper 2 plus ethylene diamine giving you ethylene diamine copper 2 plus ion. And if copper 2 plus combines with 2 methylamines, you will get dimethylamine copper 2 plus ion. In first equation, the bidentate ligand ethylene diamine forms a chelate complex with the copper ion. Chelation results in the formation of a 5-membered ring, but in equation 2, you can see there are 2 copper nitrogen bonds. As number of copper nitrogen bonds are same in chelating ligand and in monodentate ligand, hence the enthalpy of formation of copper nitrogen bonds is approximately the same in the 2 reactions. Here you can see there are two copper nitrogen bonds. When copper 2 plus is attached to two monodentate ligands, and there are two copper nitrogen bonds when copper 2 plus is attached to bidentate ligand ethylene diamine, forming a ring. Under conditions of equal copper concentrations and when the concentration of methylene diamine is twice the concentration of ethylene diamine, the concentration of complex 1 will be greater than the concentration of the complex 2. Now, this effect increases with the number of chelate rings. So, the concentration of the EDTA complex, which has 6 chelate rings, is much higher than the corresponding complex with 2 monodentate nitrogen donor ligands and 4 monodentate carboxylate ligands. Thus, the phenomena of chelate effect is a firmly established empirical fact. Now, the question arises, what accounts for the special stability of chelates? Actually, their stability stems from the additional entropy obtained when they are formed. This leads to a large negative delta G, that is free energy, which is equivalent to a large equilibrium constant for the formation of the chelate. The thermodynamic approach to explaining the chelate effect considers the equilibrium constant for the reaction. The larger the equilibrium constant, the higher the concentration of the complex. Here we can see two equations, copper 2 plus binding with ethylene diamine and methylamine. If we write in concentration forms, then concentration of ethylene diamine copper 2 plus will be equal to constant beta 11 into concentration of copper 2 plus into concentration of ethylene diamine. Similarly, concentration of dimethyleneamine copper 2 plus will be equal to equilibrium constant beta 12 copper 2 plus into concentration of methylamine 2 whole square. The square brackets here indicate the concentrations and the subscripts to beta indicate the stoichiometry. That is, beta 11 represents 1 ion of copper 2 plus and 1 of ethylene diamine, and beta 12 represents 1 ion of copper 2 plus and 2 molecules of monodentate ligand methylamine. When the analytical concentration of methylamine is twice that of ethylene diamine and the concentration of copper is same in both reactions, the concentration of first complex is much higher than that of the second complex, because beta 11 is much greater than beta 12. An equilibrium constant K is related to the standard Gibbs free energy delta G naught by the equation delta G naught equal to minus RT natural log K, which is equal to delta H naught minus T delta S naught. Here R is gas constant, T is temperature in kelvins, delta H naught is standard enthalpy change of the reaction, delta S naught is standard entropy change. It has already been explained that the enthalpy term should be approximately the same for the two reactions. Therefore, the difference between the two stability constants is due to the entropy term. Let us have a look on the two equations again. In equation 1, there are two particles on the left and one on the right, whereas in equation 2, there are 3 particles on the left and one on the right. This means that less entropy of disorder is lost when the chelate complex is formed than when the complex with monodentate ligand is formed. This is one of the factors contributing to the entropy difference. Other factors include solvation changes and ring formation. Now, some experimental data to illustrate the effect are shown in this table. These data show that the standard enthalpy changes are indeed approximately equal for the two reactions, and that the main reason for the greater stability of the chelate complex is the entropy term, which is much less unfavorable. In general, it is difficult to account precisely for thermodynamic values in terms of changes in solution at the molecular level, but it is clear that the chelate effect is predominantly an effect of entropy. A similar argument could be made for any equilibrium involving the replacement of the monodentate ligands by polydentate ligands. Reaction tends to favor the chelate. Here you can see that each ethylene diamine molecule replaces two ammonia molecules. Therefore, the number of particles in the reaction mixture is increased when the reaction goes from left to right. In most cases, an increase in number of particles increases the possibility for randomness or disorderness. Therefore, when the reaction goes to right, there is an increase in entropy, that is, delta S is positive. At the same time, the reaction involves very little change of internal energy U or enthalpy H, because the bonds are similar, that is, all consist of a nitrogen atom coordinated to a cobalt atom. 6 nitrogen metal bonds in hexaamine cobalt 3 plus are broken, and 6 new nitrogen metal bonds of about the same energy are formed in tris ethylene diamine cobalt 3 plus. Therefore, we can say that delta H is approximately equal to 0. The spontaneity of a reaction depends on delta G naught, which equals delta H naught minus T delta S naught. But as you know that here delta H naught is equal to 0. Therefore, delta G naught will come out to be minus T delta S naught. So, for this equation, the entropy change is positive, hence delta G is negative and the reaction is spontaneous from left to right. The fact that the equilibrium for the reaction favors the chelate tris ethylene diamine cobalt 3 plus means that the chelate has thermodynamic stability. The chelate effect is usually most pronounced for 5 and 6 membered rings. Smaller rings generally involve excessive strain, while increasingly large rings offer a rapidly decreasing advantage for coordination to the second site. Naturally, the more rings there are in a complex, the greater the increase in stability. If a multidentate ligand is also cyclic and there are no unfavorable steric effects, a further increase in the stability of its complexes is observed. Favorable entropy changes can again be invoked to explain this macrocyclic effect. So, now you are able to understand the greater stability of chelating complexes than the complexes with monodentate ligands. So, in the end of this lecture, let us revise what we have learned today. Today, we discussed classification of ligands on the basis of number of donor sites, chelate complexes, the chelate effect and the thermodynamic stability of chelate complexes. In continuation, in next lecture, we will discuss coordination sphere, ionization sphere, coordination number and stereochemistries for various coordination numbers.